All right, let's dive straight into this explainer and demystify the black box of artificial intelligence by looking at the fundamental blueprints of neural networks. I mean, we interact with these incredible systems literally every single day, yet for a lot of us, the underlying mechanics remain kind of obscured. So, today, we're going to break down the actual architecture of how these networks are built, node by node and layer by layer. We constantly hear terms like neural networks, deep learning, and backpropagation just thrown around in the headlines. But if we strip away all the buzzwords, how exactly do these systems map incredibly complex data and learn to make accurate decisions? Like, how do they actually know where to draw the line between one category and another? Section 1. Visualizing machine learning. To truly understand the math, we first need to see the magic. And this beautifully illustrates the whole point. What you're looking at are decision boundaries, essentially the map a neural network creates to separate different types of data. And here is the crazy part. By adding just a single hidden layer of units to a network, we drastically change how it can separate and classify that data. We instantly move from drawing rigid, straight lines to creating these highly flexible, dynamic boundaries. It's absolutely fascinating to trace this progression. As we expand the width of that single hidden layer, meaning we just add more units to it, the network's mapping capability completely evolves. It starts off by drawing a basic diagonal band across the data. But add a bit more capacity, suddenly it can enclose a specific grouping, creating what we call one pocket. Add even more units, and it effortlessly carves out highly complex boundaries, like two distinct pockets, or it even completely isolates four separate Gaussians, which are just distinct, complex clusters of data. So the architectural choices we make directly dictate the boundaries the network can even understand. Section 2. Designing the architecture. Now that we've seen what these models can build, it's time to pop the hood and look at the actual engine. Constructing a neural network is honestly just like erecting a physical building. You can't just throw parts together and hope they stand up, right? You have to consciously make four major design decisions. First, depth. How many hidden layers is the network going to have? Second, width. How many units or neurons will sit inside each of those layers? Third, nonlinearity. What type of activation materials or functions will dictate how signals pass through? And fourth, the ultimate objective function. How will the network actually measure its own success or failure? Following the flow of information through these architectural choices reveals exactly how a network thinks. Starting at the bottom here, raw inputs feed into hidden linear layers where they get multiplied by weights. But then they pass through non-linear activation functions, and this is the absolute crucial step that gives the network its flexibility. Finally, the data reaches an output layer to make a prediction, which is immediately evaluated against our chosen loss function to see just how wrong or right the network really was. Section 3. Choosing activation functions. Let's zoom in on that third design decision, the nonlinearity. Because choosing the right activation function is precisely what gives the network its ability to handle complex, nonlinear data. Without it, your neural network is basically just a giant, fancy linear regression model. Historically, early networks relied really heavily on the logistic sigmoid function, which you can see on the left. It takes any input and just squashes it into a smooth curve between 0 and 1. Alternatively, there's the tanh function on the right, very similar in shape, but it shifts the data range to sit symmetrically between -1 and +1. For a long time, these were the absolute standard building blocks. But here's the real game changer. Modern vision tasks and complex networks often swap those traditional curves out for something surprisingly simple: the rectified linear unit, or ReLU. Notice how this function is completely linear for positive numbers, but it has a strict, hard cutoff at 0 for any negative numbers. It seems almost too simple, but this creates sparse outputs, literally forcing many nodes to output true 0. That makes computation highly efficient, and famously, it helps combat the vanish ingredient problem, basically stopping the network's learning process from just stalling out completely. Oh, and there's also a soft version of this called the soft plus function, which is just a smooth approximation. Section 4, defining the objective. Okay, so once our architecture is built and our activation functions are set, we have to tell the network how to measure its own success. This brings us to the fourth design decision, and these objective function choices map beautifully back to classical statistics. If the network is solving a regression problem, so predicting a continuous number, we use a quadratic loss, also known as mean squared error. It's the exact same objective used in basic linear regression. But if it's doing classification, choosing between distinct categories, we use cross-entropy, or negative log likelihood. And critically, doing this requires adding a softmax layer at the very end of our network to convert those raw outputs into proper usable probabilities. Section 5, How Networks Actually Learn. So we have the blueprint and the objective, but a blueprint alone doesn't build the building, right? How does the network actually train itself to minimize errors and draw those brilliant decision boundaries? Well, the fuel that actually makes this engine run is a process called stochastic gradient descent. The network calculates its error and then takes small steps mathematically opposite to the gradient of that error. To figure out the direction of that gradient across layers upon layers of neurons, it relies on a fundamental principle of calculus, the chain rule. This allows us to compute complex derivatives by simply summing over all the intermediate quantities in the network's computation graph. Now, to compute those massive, complex gradients, we have to choose our mathematical weapon. We could use symbolic differentiation, the classic method you learned in high school calculus. It's easily interpretable for sure, but computationally dangerous. You risk exponential computation time if it's not implemented perfectly. Or we could try forward mode automatic differentiation. But while it's fast for many outputs, it is agonizingly slow for high-dimensional inputs, which leaves us with the ultimate solution, reverse mode automatic differentiation. It calculates partial derivatives in time perfectly proportional to the original computation, making it incredibly fast for systems with high-dimensional inputs. And this leads us to the absolute breakthrough. The hero of modern machine learning is that third method, reverse mode autodiff. When you apply this specific mathematical technique to a neural network, it is famously called backpropagation. This is the whole shebang. It gives us a fast, efficient way to take the error calculated at the very end of the network and trace it all the way back through thousands or even billions of inputs, slightly adjusting the weights at every single step. It is just incredible to think about. The basic high school calculus rules, scaled up through the elegant efficiency of backpropagation, literally power the world's most advanced artificial intelligence today. We've gone from drawing simple diagonal bands to mapping the unbelievable complexities of human language and vision. Understanding this foundation leaves us with one really big question. As we continue to push the boundaries of depth, width, and nonlinearity, what incredibly complex problems will these architectures conquer next? Thanks so much for joining me on this explainer. Keep learning, and I'll catch you next time.